So the next thing is random variables, of which I think it should be known by now, so we wouldn't go through random variable, discrete random variable, continuous random variable, moment generating functions. All of these are treated. So correlation coefficient is done in regression, so we wouldn't have to worry much on that. So our main thing is stochastic processes. Okay, stochastic processes. So stochastic processes, that's the thing we need to know. So we'll do the introduction and then we'll move into stochastic processes. So a stochastic process is a model that evolves in time or space objects to probabilistic laws. Okay, so stochastic process also proceed randomly in nature rather than consider fixed random variables x and y, or even sequence of IID random variable. We consider sequences of these random variables, okay, at different time points. Okay, so in general the value of st might depend on the quantity that at the time t minus 1, right, or even the value of that for other times. Okay, so what we are saying is that instead of previously considering only a fixed one variable, one random variable, now we want to look at different random variables at different time points. Okay, and the times are sequential. Okay, all right. So what is a stochastic process? So a stochastic process, or a random process on probability space, that is a family of random variables. Okay, so it's a family of random variables indexed by time. Okay, indexed by time, a family of random variable indexed by time. So where t is belonging to a certain time domain, so capital T is just a time domain. Okay, so where t belongs to an index time, which is t, the parameter t which is in that is usually interpreted as the time domain, or the time set for the process. So the set of values that can be taken by the random variable st is called the state space of the process. Okay, so what are the possible values that st can take? Right, like sample space. So what are the possible values that st can bring up? All right, those values are in the state space. Okay, so therefore intuitive notion of a stochastic process is that of a random system whose state at time t is st. Right, so some examples of stochastic processes are random walk, Markov processes, Poisson processes, renewal reward processes, regenerative processes, branching, queuing theory, and Werner processes. Okay, so these are all examples of stochastic processes. So what we are saying is that at first we are considering a certain fixed random variable. Okay, so let's see, we are just looking at x as our random variable. Now here this x is fixed, it doesn't change, it doesn't vary, so it's like we are looking at a random variable which varies. So that's what we say we have a family of random variables, so we're having only one random variable, just like that. Okay, and then we are trying to extend this idea to a stochastic process, and now we say that no, we don't want, let's look at this random variable at a certain time not, and then look at it as at a certain time 1, look at it as at a certain time 2. All right, so generally let's look at it at a certain time xt. Right, so it's an extension of this, where this one we just look at x, we don't look at it the changes with respect to time. Right, but now we're trying to look at it at different time point. Okay, so you can see that this is just a family of random variables. Okay, and it is indexed by time, and it can change. It's not always time. Okay, it can be volume, it can be any spatial dimension. Okay, right, but mostly we deal with time, right? So which is indexed by time, and then we will call this one a stochastic process because it's a family of random variable, but this is just a single random variable, but this is series or sequence of random variables, or family of random variables, and they are indexed by time. Okay, so that's the definition of a stochastic process. That's the definition of a stochastic process. So we have two types of stochastic processes: the discrete time processes and then the continuous time processes. Okay, so the discrete time processes, so DTP, you have the discrete time processes and then the continuous time processes. All right, so what is a discrete time process? So the discrete time process, we are saying that the numbers, the time point thing, it changes or it takes, it's a discrete, it's a finite or a countable time or numbers. Okay, so in that case we are saying that it can only take numbers which are from 0, 1, 2, 3 up to infinity, and we are looking at a finite situation where the time point might end at somewhere or countable. So either it's finite or countable, we are okay with that, right? So that's a discrete time process. It can be S0, S1. It's a random number recorded at every time 0, 1, 2, 3. So what I'm saying is that for discrete time process, the time domain is purely whole numbers starting from 0, 1, 2, right, in that order. All right, that's it. So that is the values it will take. So it's like there's this random variable x, and we are trying to look at what happens to x at time 0, what happens to x at time 1, what happens to x at time 2, and then what happens to x at time n. Okay, that's what we're trying to do. So that's basically a discrete time process. So the continuous time process, the time domain is not finite, and is also it's not finite, and it's kind of uncountable. I think this I don't see it as right. Uncountable. It should be uncountable. Okay, so we are trying to look at it in a way that it takes values other than just whole numbers. It can take decimals, it can take any elements. Okay, so if I say my time domain is coming from 0 inclusive to infinity, means everything within that interval it can take. Negative 0.55, everything. Remember time, so we are looking at the positive domain. All right, so anything that is inside that domain, it can be picked. Okay, so we say that that's a continuous time process, ST, which is coming from a T, has a random value recorded at every instant in time. Okay, so every instant, within this, every instant, the random variable is measured in there. Okay, so none of the instants are removed. Okay, so state space. So the state space X is a set of real values that ST can take. So remember that we said that if you have one single random variable and you are performing an experiment on that, then that random variable has a sample space, also known as a state space. So the fact that there is a sequence of those, or a family of that random variables, there is also going to be that state space, the values that st can take. Okay, all right. So I think that is it. We'll continue from state space